All right, let's look at another more complicated example. So in this case, I have h of s equal to negative 1,000 times s plus 2 over s times s plus 200. Now, before you watch this video, you might want to watch the one about the constant k, which talks about how to deal with a negative sign. You may also want to look at the video that talks about poles and zeros at 0, which will tell us how to deal with this pole at s equal to 0. Okay? So let's follow through our typical steps. So step 1, determine the pole and 0 locations. Okay, so step 1. So we remember that zeros are the values of s for which h of s is equal to 0. So in this case, it would be s equal to negative 2. And my poles are where h of s goes to infinity, which would be at s equal to 0 and at s equal to minus 200. So if I look at this, again, I like to draw my pole 0 plot. So this is my imaginary part of s, and this is my real part of s, like that. Okay, so I have a pole which I mark with an x at 0. I have another pole out here at x equal to, so s equal to minus 200, I put another pole, so that's another x. And then I have a 0 here at minus 2. Okay? All right. So that's our basic graph. It shows the relationships of these. Now we remember that our inputs to these systems, so if I had a circuit that had that transfer function, then what I care about is if I put a sinusoid into that guy. So a sinusoid means that I'm putting in something related to e to the j omega t, which means I care about h of j omega. Okay? I plug in s equal to j omega when I have these types of inputs. So that would turn this thing into negative 1,000 times s plus 2 over s times s plus 200, like that. Okay? And I should be plugging in j omega when I do that. So j omega plus 2 on top and on the bottom, j omega times j omega plus 200, like so. Okay? So when I plot the magnitude of this particular transfer function, what we have learned is that the magnitude of that transfer function changes or breaks at the frequencies or certain frequencies that are caused by these poles and zeros. So the break points in this case where the magnitude would change would be at 0, 2, and 200. Okay, those are my breakpoint frequencies. All right, so I either break such that my plot goes up or goes down at each of these frequencies. Whether I go up or go down depends on whether or not I'm looking at a pole or a 0. Okay, so now I know my breakpoint frequencies. Okay, so now I want to get my transfer function in the correct form, so something like this. And now I want to get into step 2. All right, so in this particular case, okay, I want to get my h of s, which is minus 1,000 s plus 2 over s times s plus 200. All right, I want to get that into some form of k times tau z s plus 1 over s times tau p s plus 1. So in other words, I need to know what k equals, tau z equals, and tau p equals. All right, so I got to factor my original transfer function to try to figure that out. All right, so this becomes negative 1,000 times 2 times s over 2 plus 1. Again, if I distributed the 2 into this s over 2 plus 1, you should see that I get s plus 2. And then on the downstairs here, I have s times 200 over, or times s over 200 plus 1. So if I distributed the 200 into this s over 200 plus 1, I would get s plus 200. Okay, So to simplify that, I have minus 1,000 times 2 divided by 200, which should give me minus 10, okay, because I have minus 2,000 divided by 200. So I should have minus 10, make it clear that's a 10, times s over 2 plus 1 over s times s over 200 plus 1. So looking at this, my k is negative 10, or remember that's 10 with an angle of 180 degrees. My tau z is 1/2. My tau p is 1 over 200, right? So this guy comes from the pole at s equal to minus 200. This guy came from the 0 at s equal to minus 2. Okay? All right. So we're going to look at trying to graph this guy. Now I get this negative sign in here. So my k value is negative. Nothing wrong with that. You can watch the video on these constants. So I've got a separate video on that. Remember, because I'm plotting 20 log of the magnitude, right? The magnitude of negative 10 is 10, all right? So the fact that I have this minus sign changes only the angle of h of j omega, and we're not concerning ourselves with the angle, all right? Okay, so let's get into step 3, okay? So step 3 is to plot the individual contributions of my 2 poles and my 0, okay? So let's start with the 0, all right? So I have a 0 at omega equal to 2. So the first question is, where is omega equal to 2? All right, so here is my sort of graph that I've drawn. And again, I marked it off as I always kind of do. So at the origin here, 0, corresponds to omega equal to 1, right? The log of 1 is 0. The log of 10 is 1. The log of 100 is 2. The log of 1,000 is 3. The log of 10,000 is 4. The log of 0.1 is negative 1. The log of 10 to the minus 2 is minus 2, right? So I see that each of these tick marks represents a decade in frequency, so a factor of 10 in frequency, which are all linearly spaced, all right, on this axis, okay? So we're going to do the 0 first. So the 0 happens at 2. Now where is 2? Well, that's somewhere between 1 and 10, right? So it's got to be somewhere between 1 and 10. But where? All right, so to know where, the simplest thing for me to do is to do the log 10 of 2. So the log 10 of 2 is 0.301. So that would be about a third of the way between 1 and 10. So somewhere around, I don't know, right about there, okay, is where 2 would be. Now, 20 would be a decade after that. 200 would be 2 decades after that. So suffice it to say, I probably can predict already that if 2 has a log that's equal to 0.301, if I did 20, that's probably going to be 1.301, and it is. So where is that here? So 1.301 would be about a third of the way between 10 and 100. Okay, so this would be 20. And if I looked at log 10 of 200, that would be at 2.301. So again, about a third of the way between 100 and 1,000. So that would be 200. And while I'm at it, why don't I also put in here log 10 of 2,000, which is going to be at 3.301, which is about a third of the way between 1,000 and 10,000. So that would be, I don't know, right about here. All right, that would be 2,000. Okay? All right. All that said, let's get started. So let's do our 0 here. Okay? I'm going to do my 0, and I'm going to do that in yellow. So what do we know about zeros? So if I'm drawing the magnitude of a 0, the log magnitude of 0 for frequencies lower than the 0, and the log magnitude rises at 20 dB per decade after. Okay? So this guy's going to be flat right up until I get to 2. and then it's going to start to rise. So as I go 1 decade further, so from 2 to 20, I'm going to rise up to 20 dB. And as I go from 20 to 200, I'm going to rise up to 40 dB, like that, and keep going. All right, so this guy is going up at plus 20 dB per decade. Okay, now I'm going to move to my first pole. Okay, and I'm going to do this guy here, the pole that exists at 200 radians per second. Okay, now for a pole, same thing. Okay, for a pole, my magnitude is 0 for frequencies lower than the pole and then falls at 20 dB per decade for everything after. So I'm going to be flat. And then at 200, I'm going to start to fall. So since I fall at 20 dB per decade, from 200 to 2000, 1 decade, I'm going to fall 20 dB. Okay? And then wherever, if I marked off a little bit further, right, here's 5, which is 10 to the 5th. So suffice it to say, if I looked at 20,000, that would be somewhere about here. And at that point, I should be at about minus 40 dB per decade, or minus 40 dB at that point, because I'm falling 20 dB every decade. Okay? All right, now I have to deal with the other special case. So in this one I've got also a pole. Right? This guy has a pole at s equal to 0. So we said we had a pole at s equal to 0. That guy's always falling. All right, and he crosses through the origin. All right, so we did that before. So let's add in him here. Okay, there's a whole separate video on checking that one out. I'm not gonna do it here. All right, so this guy falls like this. Okay, all right, and that's now the individual contribution of each particular component. Now I get to my step 4. So my step 4 is to add the contributions of each of these individual guys, moving from left to right. All right, so let me do that with red. All right, so over here, so as I say moving from left to right, so if I started right here, let's say at 10 to the minus 3, I have 0 plus whatever this is. So obviously this guy dominates. So I'm going to draw it over top of this. Okay. And I'm going to follow this guy until I get to omega equal to 2. Once I get to omega equal to 2, at that point, I have a pole that is pushing me down at 20 dB per decade and a 0 that is pushing me up at 20 dB per decade. So I level off. Okay. I level off until I reach this other pole. Once I reach that other pole, I start to fall again at 20 dB per decade. So the red there is the overall combination of all of the poles and zeros in this problem. Now there's one more step, step 5. Okay? Step 5 is to basically shift everything up or down based on the k value. Well, my k value in this case was negative 10. 20 log the magnitude of that is, so 20 log 10 of the magnitude of minus 10 is equal to 20 log 10 of 10, or 20 dB. So that means I need to shift the whole graph up by 20 dB. So to do that, and now I'm going to go back to black. So right here at 0, right, so when omega is equal to 1, my red graph was at 0 dB. So I need to shift that up to 20 dB. Okay, and here at omega equals 0.1, I was equal to negative 1, so I need to be equal to minus 40 dB, or sorry, plus 40 dB. So my overall graph is going to look something like this. It started moving on me here. Okay, so it's parallel. Everything is shifted up. So this is plus 20. Okay. And one thing I want to be careful about is where at what point, all right, what is the value, I guess, at 2 where this guy should level off? So one thing I want to check for myself is what is the value here? What is the height of that guy? Well, one thing I can do is I can say to myself, okay, the change happens at omega equal to 2, or log 10 of 2 on the log scale is 0.301. Because this graph here was falling at 20 dB per decade, if I do minus 20 times log 10 of 2, I see that the value here had to be minus 6.0206. Okay, so I take that value and I shift it up by 20, which puts me at 13.97. Okay, so which would be somewhere right around here. Okay, right around there. And then I level off at 13.97 until I get to the 200 again. Once I get to the 200, I start falling like so. So notice I shifted the whole graph up sort of a constant amount throughout. Okay, I shifted the whole graph up by 20 dB. Okay, all right, so for us at this point, we are basically done. All right, so now I've made my graph and I am done. So we'll use that again maybe to figure out magnitudes at specific frequencies in a different problem.